Hi, my name is Obadiah Valdez, and is my partner Fadi Shaba, and we're both mechanical engineering majors in the Jacobs School of Engineering. And so our project was efficient water harvesting from atmospheric air using optimized polyelectric hydrogel, and we conducted this project under Professor Chen. And so this year we conducted research to determine what is the optimum combination of absorption time and desorption time for hydrogel to absorb water from the atmosphere. And this allowed us to compare its viability against other materials that are used in atmospheric water harvesting. And we hypothesized that our current choice of hydrogel set to certain parameters of temperature, thickness, humidity, and time will outperform other competitors and rapidly absorb and desorb water from the atmosphere every 20 minutes throughout the day. And so, as we've seen, like in recent years, climate change has increasingly caused the drought and other, stress to our water supply. And Earth has roughly 2.5% of its water as fresh water, which we use for drinking and other uses as well in everyday tasks. And because our freshwater supply is decreasing, we have to find good alternative ways to obtain this water. And so the problem with trying to find a good alternative is that most solutions can either take up too much energy, too much time, or too much materials and costs to be able to implement these processes. Examples of these have been desalination from seawater, which would just would separate the salt from the water to get pure water. Cooling ambient air, inducing condensation to the ambient humidity, and using other materials and desiccants such as silicon gels, zeolite, and other materials that try to absorb and desorb water as well. The problem with these is that, again, too much energy for its low yield, especially compared to our choice of hydrogels, which is a cross-linked network of hydrophilic polymer chains. And as you can see in figure 3, that is a microscopic view of this chain or framework of hydrogel. And our research lab has been investigating this because specifically hydrogel, it has an enormous surface area that can absorb up to 420% of its weight, and that it has a very high affinity for water, so it's very porous. And this is very important because hydrogel is laid out in thin layers. As you can see in figure 1, it is an aluminum foam that is actually coated with a thin hydrogel layer. And as you can see, it's just like a square, or square of this. And because of this, its low weight is beneficial to use in water harvesting. And so our methods for conducting an experiment to find the optimum times. First, we prepare foam that is coated in this hydrogel. We then place on a hot plate to raise the temperature of the hydrogel coated foam, which starts the absorption process. And after we collect data based on its absorption of water and its desorption as well, we then model this. We model the graph that we will show later. And we find the necessary parameters to find the greatest amount of yield in an average setting. And so an average setting in San Diego is about 60% humidity. And after modeling, we figure out the ideal cycle for absorption and desorption that is most efficient.
So like Obadiah said, our project sought to determine the optimum absorption and desorption cycles of hydrogel-coated graphite foam. To the right is the raw data of the absorption and desorption at 22 and 35 degrees Celsius respectively, both at 90% relative humidity. So we got our data and then decided to plot it on MATLAB over a 190-minute period, 120 minutes of that being absorption and 70 minutes of that being desorption. From the graph, it is clear that most of the water is absorbed from the beginning of each process. As time increases, the curves begin to plateau From this, we decided that it's honestly only like important to look at the first like 30 minutes of each process, as time increased a lot, the amount of water absorbed compared to the amount of time that it took wasn't like really like useful. And with this, the rate of change was highest at the beginning. We used linear approximation to determine the average rate of change of different combinations of absorptions and desorption times. Like for example, we like looked at 30 minutes absorption and 10 minutes of desorption, or like 5 minutes absorption and like 5 minutes of desorptions. And using linear approximations, we found the optimum cycle, at least at the beginning, was 15 minutes absorption and 5-minute desorption. Scaling this to a 24-hour time period, we found that it yielded 17.48 grams per gram of water in the 24 hours with 72 total cycles. While this is like a good beginning, we still have to take into account a lot of other things. One of those being that while we use linear approximation, this curve actually can be fitted to the diffusion equation. And while we don't have the skills to do that yet, we've been working on that with our lab to come up with a good model. We also have to take into account how after each cycle, water is still like left in the hydrogel, which will increase the amount of water absorbed over the 24-hour time period. Other than that, our next steps would also be looking to increase the amount of water absorbed in different ways. Like at the beginning of this process, we were also looking into the kinetics and thermal conductivity and how to increase that. In this case, we used the graphite foam, which helped increase the kinetics, but we could also use many other materials. And then we would also like to make the cycles more energy efficient, as like the main point of this project is to try to make this energy efficient, as other uses of other like forms of desalination and ways to harvest water isn't the most energy efficient. And using this, we like injected it with like different temperature, which used energy, but ideally we would like to use the sun's temperature.
And so we wanted to acknowledge our professor, Renfrew Chen, and our graduate student mentor, John Zan, for giving us the opportunity to work in their lab and for teaching us so much, especially our graduate mentor. He met with us, I think, almost every Monday to try to help us with this project. And he gave us a lot of our research and a lot of our data as well. He was a great help to us. And we'd like to thank them for that. And we'd also like to thank VED for providing us with much needed guidance throughout this project, especially during this post-year, because it was, I guess, a big project. And we'd also like to thank the entire year program staff for also providing us the opportunity to be in this program. And thank you for listening.